So let's continue arbitrary loading. So here I have some load, arbitrary load. So this is time, this is some force magnitude. So this is my arbitrary load. So now I want to see the response of this arbitrary load. So what I am trying to do, I will take this function, forcing function, and I will split into small strip. So this one is called this distance at what time we are taking the strip is tau, and the small distance, small time interval is d tau. So this is represented as, so this is delta of t minus tau. So from the magnitude will be, this is f naught, f of tau, this is f. So this is the function of f of t. So therefore f of tau into d tau will be the magnitude of this delta function. So we will multiply f of tau into d tau. So for response of this delta function, so we already know it is h of t. For delta of t, it is h of t. For delta of t minus tau, it becomes h of t minus tau. So this is at the single point. So this is at this single strip. So what about rest of the strip? So we need to integrate it. So then we will integrate this. This is dx of t. So then for x of t, what we need to do, x of t, we need to integrate this minus infinity to infinity. Here minus doesn't matter, so doesn't have any meaning. So 0 to infinity, here it is time. So instead of doing it, we will say t1 to t2, t1 equal to 0. So then we will write f of tau delta of t minus tau d tau. So this is the equation. So what this says, so this says we have some function, some arbitrary function. So we will take one strip and we will model this as a model this as a impulse load. For impulse, so how it will be, impulse we have a response delta h of t that will goes like this. So maybe like this, and next point, so nearby point there will be another impulse, so that will also goes like this, therefore another impulse. So then if we combine everything, if we combine the response of x of so if we combine the response of f of tau d tau delta of t minus tau of all the tau equal to 0 to, so whatever the number of tau we split, then it will be, this will be response of arbitrary function. So this integral called Duhamel integral. So now, so sorry, this will be h of t, this will be h of t, yeah. So now we write the complete solution. The complete solution will be x of t will be e power minus eta omega t a cos omega dt plus b sin omega dt plus this Duhamel integral. So which one? 0 to t f of tau h of t minus tau. So this is d tau. So now we have boundary condition x of 0 equal to 0, x dot of 0 equal to 0. So now we substitute this boundary condition. So we will take derivative x dot of t. So that becomes e power a sin omega dt into omega d. This will, there will be minus plus b cos omega dt into omega d minus neta omega e power minus neta omega t a cos omega dt plus b sin omega dt. So then we need to take derivative of this one. So for that we need some rule called Leibniz rule. So because if we have an integral I of x will be, this is a of x, b of x, f of x comma tau into d tau. So this is the form of integral. So if we take derivative di of x by dx, this will be, so a of x, b of x, dou f of x minus tau by dou x into d tau. Then we need to take the derivative of these two limits. So db by dx into f of x comma b of x minus dA by dx f of x comma a of x. So this is the equation. So now we substitute this into taking integration of this value. So we will write same, limit will be unchanged. So then we need to take derivative of this one. So this becomes dh of t minus tau into dt. So f of tau doesn't have t, so it will be, it act as a constant. So then d tau, then derivative of t becomes 1. So then we can write f of t minus tau. So f of tau will be there, h of t minus t. So t becomes 1. So t becomes, which one becomes, tau becomes t. So tau becomes t, therefore h of 0 equal to 0. So h of 0 will be, okay, we will find whether writing the last term dA by dx will be dA is equal to 0. So this terms will be 0. So here h of 0 will be 0. So if you put t into h term, so we hope we have derived before. So if we put, where suddenly apply load h, so this is h of t. If we put 0, so h of t, h of 0 equal to 1 by m omega d, sine of 0 will be 0. So that's why it's 0. So now you might know why h of 0 equal to 0. So therefore we have x dot and x dot now. Now we substitute the boundary condition. So this leads to a, this leads to a plus integral 0 to t f of tau into h of 0. This limit also becomes 0. So this limit becomes 0, therefore this term becomes 0. So therefore x naught a becomes 0. So if it is x naught, if the boundary condition x of 0 is x naught, then a equal to x naught. So let's see for the velocity, x dot of 0 equal to, so b omega d minus neta omega a plus this rest of the things also get 0. So this leads to x naught dot, so therefore b equal to x naught dot minus neta omega x naught divided by omega d. So therefore for x of, so this is for if x of 0 equal to 0, then b is also 0. So therefore for for arbitrary function, the total solution will be 0 to t f of tau h of t minus tau d tau. So will be the complete solution of this arbitrary function loading. We will see some remarks on this Duhamel integral. So far we have seen, so what is the, for arbitrary function, so what will be the response. So therefore response will be 0 to t f of tau, so where f of tau is this amplitude f of tau. So at tau, so there is a small strip d tau, so f of tau into response of t minus tau into d tau. So this one is the response at x of t, at some t. So here, so this is x of t, so this is the value. So what is the response up to the until the function t. So now to get the full response, we need to integrate throughout the f of t. So the full response will be 0 to infinity f of tau h of t minus tau into d tau. So you will get the full complete response. So now this kind of system is called causal system. So what that means? That means the system only will respond after you are giving the signal. So this is t and this is the function, forcing function. So I'm giving the force from the 0, some arbitrary force. So therefore before, so if you draw the deflection response, this is like, let's say this is response of x. So before it will be 0. So until t is equal to 0, the system will be 0, then the response will be something like this. So this kind of system is causal system. So if we take this values, like what this values when t equal to less than 0, less than or equal to 0, f of tau, f of tau equal to 0. So now here tau means t, f of t equal to 0. Similarly h of t is also 0. So so therefore we can write this response function into minus infinity to plus infinity f of tau h of t minus tau d tau. So now there is a symmetry exists. This minus infinity to plus infinity leads to symmetry. This symmetry leads to the convolution. So what this convolution, this above integral is called convolution integral. So it says above integral is Duhamel integral, and this is equivalent to the convolution h of t into f of t. So this star means convolution. The second one is is the convolution has the property of commutative. So it's a mathematics. So I'm writing this response t minus tau f of tau d tau. So I'm doing variable change of variable. So I'm doing this t and I'm taking derivative. So where tau is constant, see t is constant, tau is variable in this integral. So it is minus d tau du. So now substitute these things in above integral. So minus infinity to plus infinity. So then h of u f of tau equal to t minus u into d tau equal to du minus, right? So then you can take this, you can write these things t minus u. So you can, so we will take that minus from, yeah, so we need to change the limit, apply the limit also here. If you put the limit when tau goes to, when this, yeah, so this is u and v relations. So when, so we will integrate these things, so it becomes minus tau equal to u, applying the limit. So here the tau is minus infinity to plus infinity, thereby we will get, so sorry, so yeah, so when tau goes to infinity, this u goes to minus infinity. When it goes to minus infinity, we will get plus infinity. Therefore we will get things like this. This minus will come here, so therefore it becomes like this, h of u f of t minus u du. So this will be called h of t convolution f of t, sorry, f of t. So f of t convolution h of t. So this is x of t. So that's why, so here we proved its convolution. So these are the two important property of this Duhamel integral, and this is very important, not only in terms of arbitrary function, but when we go for multi degree of freedom system and continuous system, this will be very handy.